that it's recording. Okay, so let me share the screen again. Okay, so there's one thing again. There's one thing that I didn't consider. So even if this one is the choice of of the of the choice of the host, we are saying that there is we include the information of the door that is being chosen by the player. So in this case, the player has chosen door 2. Okay, so that means that, okay, let's put that one again. So we were asking the question of why is this why is this why is this one? Yeah, that's the question. Otherwise we'll be okay already. Okay, so door 2 is the one that's finished, that's chosen by our player. Yeah, so this is door 2 chosen by our player, and we know that uh, the car is in door 1. So in this case, the player, from the point of view of the host, the car is in door 1. Okay, and then the player chose door 2. Okay, that one we didn't include in the information. So this is door 1,
Sir,
door 2, and door 3.
sir,
Okay, so yeah, so these are the point of view of the player, of the host, but then we didn't, door in this case door 2 was chosen. Door
the,
2 was
the
supposed to be
proof.
open. I mean, door 2 was chosen because this is given that door 2, given that door 2 was chosen by the player, and then what is the probability that given was door 2 was chosen, what is the probability that the car is in door 1? Okay, so now, so if we choose this to be does that make sense? Hello, am I talking to anyone?
Sir,
Am I talking to anyone? Okay. In this case, D2, although in our definition of D2, it is open. Okay. So from the point of view of the player, that D2 is open. Okay. So, but it's still not open. Okay. It's still considering of opening D2 or some other things, some other doors that we will open. Okay. From the point of view of the player, that is the tricky part. Yeah. So here we say that D2 from the point of view of the host, D2 was chosen. Okay. So if you have, okay, maybe okay, maybe I should not where is the sharing of the screen? Am I sharing? Okay. I have to write it again. Okay. Uh, so that's the tricky part. From the point of view of this, from the point of view of the whole of the player, door 2 has been chosen. Okay, it can be opened or it cannot be opened. That is his choice. Okay. So it can be considered open. If it's open, that means there's no more switching. Yeah. If you don't open, then you go to the other door. Okay. So anyway, so we ask from the point of view of the player, we say, you choose door two, and what is the possibility that given door two, you choose door two or door two is open, what is the probability that the car is in door one? Okay. So you choose door two. Okay. And then, because one of the other doors will be opened by the host. If you choose door two, door three will be open, yes, by the host. And so you are left with door one, right? So you want to know that if you choose this one, from the point of view of the player, if you choose this one, then of course, if the car is in door one, the host will open door three, right? So
Mm.
now the question
Yes.
is, if you open door two, what is the probability that the car is in door one? If this probability is high, then you don't switch, or you switch, or you don't switch. Sorry, you switch. Okay, because you choose door two, given door two, and then the probability that the car is in door one is big. Okay, so that means if this is higher, so you switch. You should choose door one because the probability of the car being in door one is higher, given that door two is open.
Mm.
Okay. Ah, I wish we were in the. Okay. Anyway, so this is from the point of view of the player. Okay. For sure, D3 will be okay. That's the point again. If the player choose door two, and then the 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 host will open D3, and now he is left with door one. So will he choose door one instead of just choosing door two eventually without switching? Okay. So if this is high, he will transfer to door one. Okay. Now we already answered most of these questions. So
Great.
now this is zero, and the rest of them, this is 1/3. And then this is the question of why it is one. Okay. We already answered this one is 1/3, and this one is 1/2, because, okay, from the point of view, again, from the point of view of the host, you know that the car is here, okay, and then you're opening. There are only two possibilities of opening, okay, that you open door one or door two, okay. So now this one, it says that why it is one.
I wouldn't say that.
Okay. Okay, let me just answer. So if the car is in door three, so the car is here, there's nothing here. Okay. And the player choose door two, it says that you only have that's the I don't buy it. I don't buy it. So this is one because there's only one that is left by the user to choose. Oh, by the host to choose, because this is from the point of view of the host. Okay. So if yeah, I don't buy it to be one. Sorry. It looks to me like the answer is really 1/2. Okay. Anyway, so the answer, their explanation is that given that the car is in door three, okay, let's just erase this one. Given that the car is in door three, and then the player chose door two, and so the host is left with only one door to be open, door one. Okay, that's why it is one. For sure, it will open this one. Okay, so now what about this one? If the car is in door two, is in door one, if the car is in door one, okay, The host, I mean the player chose door two is the same, isn't it? The host has to choose this one. So this should also be one. It is not like that. Okay. But anyway, so they try to do a simulation and says that there are 10,000 simulations, and we say that staying uh, on the same on the same door will lower the possibility of winning, but switching will increase the possibility of winning. Okay, that's their answer. Okay, I think who was that answer? Who was that answer of me? Okay, let's end it to there. Okay, it is just an exercise. Okay, it can be you can come out with your own answers and try to make your own interpretation. But for me, I don't buy the solution that is 1 year. Okay, we used to have this one in the previous year, and we agree. The whole class agree. But now I don't agree. Okay. Anyway. Okay. Uh, okay. Let's get one down to rest. Did you agree or you don't agree? What's your interpretation? Should we agree with Mr. Musa about being one half? Because the only difference that we have is this part. This is the only part that we have that makes the difference. Okay. Anyway, let's leave it there. Okay. If you find a solution, you tell me. And yeah, I mean an interpretation, because here is just a matter of interpretation. Okay. How you interpret the term that you put the number. Okay. Anyway, let's leave it there. Okay. Let's move on to the rest of the discussion of naive Bayes rule. Okay. So we already have we had some we already discussed the example on where there's the alligator, the length of the alligator will change, and regarding the feature of the alligator being the certain length, and then we can see what is the probability of the given the body length of that it is an alligator or a crocodile. That example we have already discussed, and so we have to go through all the possibilities in order to compare. Okay, so now we are saying that the reason for this is that in the naive Bayes, we say naive Bayes because it is an approximation of the Bayes rule. Okay, so how is this being an approximation? I put it in the last slide. Okay, maybe I should put it earlier. Okay, this is the approximation. This is what happens. There are two types of approximation in the Bayes of Bayes theorem. Okay, so one type of approximation is called maximum a priori. Okay, maximum a posteriori. Okay, so in this case here, we try this is the equation of the Bayes rule that tries to approximate. I wish I really have a writing pad, where in this case, if you just consider only this part, not the argument max, so that is P of D given H and P of H, okay, and probability of D, okay? So that's the Bayes theorem. So now, if we want to know this term, we need to compute this term. Okay. Yeah. Well, that is that one. Yeah. Okay. So now we can say, we can drop the denominator. Okay? We can ignore the denominator because of this term, argument max. Okay? That means that we have to compute through all the possibilities of h. Okay? In this case, the h was the length of the alligator, or the length, the body length. Okay? Given a certain body length, and then what is the probability that it is an alligator or it is uh, uh, yeah, given a body length, and what is the probability that it is an alligator, or what is the probability that it is a crocodile. So now, so in this case here, okay, oh, so this is D is the body length, and H is the crocodile or the alligator. So this is the classification that we are looking at. Yeah. And so D is the one that is known to us. Okay. So we have to go through all the possibilities of H. So H, the big H, contains all the possibilities. In that case, the alligator and the crocodile. So D is the length. Okay. It doesn't change. H is the one that will change. The small h will change. So now the small h, so if we drop the big D, so we are left with the numerator only. And so in this case, this is the numerator. Okay. Now, this is about the crocodile or the alligator given the body. This is the given crocodile, and that is the body length multiplied the probability of the crocodile. So if this is higher, okay, you see what is, this is high, and then now you change, you determine with the alligator this time, and so which probabilities are higher. So that's why we say argument max, which argue argument meaning based on the arguments what are given or the inputs. So the inputs here are h that are changing. Okay, only the small h is changing, d is not changing. So based on the variable or based on the argument, in this case the h, whether crocodile or alligator. Okay, so you choose which of those will give you the more higher probability. In this case, I mean the higher probability because there's only two. So that is the case that of the alligator and the crocodile that was given in the previous example. Okay, so in this is the first method. Okay, in the first method, maximum a priori considers only the numerator, and then you have to go through all the possibilities to find what is the maximum. Okay, maximum probability. Then next, maximum likelihood. In this case, it's a much more simpler approximation. In this case, it's trying to remove two. Okay, so now it's trying to remove two terms. So in this case here, we are okay. So the original equation was the same as previous one, where we want to approximate uh, the probability of the h variable given the d that was changing. So in this case here, the original equation was we want to know whether it's crocodile or alligator given the dimension that is not changing. And so now by Bayes' theorem, okay, so we say that this is dimension given with the crocodile or alligator, and given the crocodile or alligator divided by the probability of the dimension. Okay, so in the previous case, we try to remove this and we say max argument, maximum argument. That means we will go through all the possibilities of the variable h, whether crocodile or alligator. Now, in this case here, in the maximum likelihood, they remove this as well. Okay. Okay. Now we are saying that to know the probability of the crocodile given that dimension, you all you need to do is just reverse. It's like reversing, yeah, and looking for which one was the higher probability. Okay. Why? That is only true if both the probability this is making the assumption of uniform prior. That means that there are equal probabilities of all the small h's. Okay, so equal probability of crocodile, equal probability of alligator, and so you can disregard it, and so this will apply. Okay, you understand? So in the previous case, there's no, in the previous case here, in this approximation, there's no, there's no assumption that being done. Okay, this canceling this out just is just uh, is valid. It doesn't make any assumption. It is valid because you are going through all the possibilities and comparing them. This factor will not matter anymore. Okay, that is a factor that you can disregard because it will not matter. Okay, there is no assumption. On the second one, we are making an assumption. We are making the assumption that the probability of each of those variables, of the arguments of the input variables, are equal, and so now you can disregard it, and so you can only, you have a very simple equation of knowing the probability of a variable given a certain dimension, in this case a dimension, okay, which one has higher probability with which variable, by just switching, okay, assuming that all the small variables, these small symbols or the variables, have equal probability. Okay, so that's the fast way of dealing with all the approximation for naive Bayes theorem. Okay, so I will leave it up to you to work through all the to some of the examples. Okay, if you have time, you can answer them. This one we have done already. Okay, we will work through the other examples when we have. We'll try to save time so that we can work through some examples after we discuss all the subject. Okay, all the topics for the class. Okay, so now let's stop here so that we can move on to the next topic. The next topic is about support vector machine. Okay. Okay. So now this is the second to the last topic. Okay. So again, we review. So we previously we have a normal regression. That means we want to approximate a function of based on a polynomial, and then given the data of x and t, and these are, it is based the method is about the error term that is expressed. In this case, this is the value of the data that is given, and the x that is also from the data, and then this is the polynomial that is uh, our approximation, and the w is the one that we are looking for. And so of course our approximation minus the value of the data will have some error, and we try to minimize that error by taking the gradient of that error. And so we say that we go through all the steps of the w's by taking the gradient. We correct our w's by taking the gradient of how the how the error is changed based on the change of each of those w's. Okay, that's how we look for the values of w's. Okay, so again, given input x and there's an approximation y, and so we want this function to approximate our given data. Okay, so now on the decision tree, the same thing. We have certain inputs. Okay, we want to know what is that function that will give us a yes or no answer. Okay, a decision. Okay, whether yes or no, or maybe there's a maybe in between. But in this case here, we build the function not as a polynomial, but the function is of a tree-like function that will give us the decision. On how to build the tree, it is based on information gain, that is based on the absolute entropy minus the dependent entropy. Okay, so the entropy that is dependent on a certain attribute. Okay, so now how do we compute that? So the absolute entropy, you have this one dependent the absolute entropy, you have this equation, and then the dependent entropy or the relative entropy has this equation. We just plug in and then that's it. Okay, we we see the information gain, and the highest information gain will be the next layer of your tree. And so that's how we build the tree. So we build the layers of the tree, and then using the highest information gain, then the next layer, you choose again the next uh, highest information gain, and so on. Okay, until your information gain, there's no more information gain, or in this case, it will become zero, or there's no more decision. There's an absolute. In this case here, if there's information, there's no increase of information, then that means that there's a classification is already done. That means one side is yes and the other side is no. Or then or that means the classification, there's zero already in one side. All the things are classified in one direction or in one classification, and there's zero on the other side. Or that means that there's only one and one on both sides. And even if you split them, it will not give you additional information. Okay, additional decision. I mean, a better decision that will help you in the final output. Okay, so now when we review the Bayes rule, it's the third approximation. I mean, the third function, yeah, approximation. So because all of these are not exact solutions, but just approximation. So in this case, probabilities. Yeah, we look at the probabilities of a certain outcome y given a certain x. Okay, so now they are given the Bayes rule, and so we just say that this is, again, I emphasize that these are known information. The right hand side are known information, and then the left hand side are the things that are unknown that we are going to consider. Yeah, given x, of course, this is known, and then given x, what is probability of a y? So in this case here, probability of a y, of a probability of an x given y, that is a known information. In other cases, these are the the one that we have considered, the sneezing and the flu. These are information about sickness, for example, medical record, and what is a probability of that person having a particular ailment given a certain parameter. Okay, so it's like a medical record in some cases. So the right hand side is known information, left hand side the ones that we want to know uh, to predict the probability of certain situations. Okay, and then we go for naive Bayes rule, and so naive Bayes rule is based on the uh, many events that are based on a certain event. Yeah. And so, for example, in or many parameters, let's say many parameters or many properties or attributes x1 to xn given an event y or given a case y. And so we say that based on the chain rule of dependence, that each of those events are independent of each other. And so we can write them as the product of all the probabilities of each parameter or each attribute given the event y or given the the case y. Okay, so this equation is based, I mean, this expression is based on the principle of chain probability of probability chain rule of probability dependence, where each of those events are independent of each other, and so we can write them as like this. Okay, so now, so given that these probabilities, I mean the events are independent of each other, we can write them independent of each other. And so there are ways that we can write the Bayes rule and also to simplify them. Okay, so we can rewrite the Bayes rule in terms of these independent parameters, as well as we can rewrite the Bayes rule in terms of these maximum a priori. That means we can disregard the denominator. Okay, and then we can simplify our term based on the numerator, the Bayes theorem. And also we can disregard totally, we can disregard an additional term of the probability of the variable, because we say that each of the variable have equal probabilities. Okay, so these are three, actually, the three cases of of variation of the Bayes rule, where in this case we have many uh, events or many parameters that are independent of each other given a certain parameter. Okay, that's first one. Second one is that we can disregard the denominator because we go through all the probabilities of all the variables that are given. Okay, then we check what is the maximum argument and we choose that variable. Okay, and the third one is that we disregard one term because we say each of the probability of the variable have equal probabilities, and so we can simplify the naive Bayes rule in this case. Okay, now let's go to support vector machine. Okay, so support vector machine in the most part is a binary classification. Of course, there are many other classifications now. Binary meaning there's only two classifications, but it's also used for many other classifications now. But initially, it is used for binary classification. And so, for example, in this picture of blue and red, okay, we want to classify the blue against the red. Okay, so it starts with a linear function. That of given a certain input variable x, yeah, of the ith data, okay, if it's greater than 0 or greater than equal to 0, then the classification is positive 1. Okay, again, given another function, if it's less than 0, the classification is negative 1. So what is that kind of function? Okay, that function, okay, maybe I'll stop asking question because it will make us. So if it's greater than 0, it's a step function, yeah? So if it's greater than 0 is here, positive x, and less than 0, less than step function, this is minus 1, and this positive 1. Okay? It's a very simple classification. Okay, sometimes in some cases it will work, of course. And then now to simplify this equation, the way to write it is that here, okay, if yi, which is the output, multiplied by the function, the function that separates the variables is greater than 1, greater than 0, then the classification is correct. It's just another way of writing this one. Why is it like that? Because the function, this function greater than or equal to 0 is 1. Okay, multiply this yi, multiply this 1. If you multiply it, it's greater than 0. Okay, here is less than 0, but yi is minus 1. So if we multiply it, it's still greater than 0. Okay, so if you multiply the classification against the function, the output of the function, then if it's that greater than 0, that means the classification is correct. Okay, so as you can see, in this case, this one can be linearly classified. Okay, that means you can draw a line to classify them. But in this case, it's hard to draw a line to classify them. Yeah, okay. Okay, the next. Why I cannot? Hello? Why I cannot change it? Okay, there. Okay, so now let's go to the next slide. So that I mentioned it already, linear separability. So it is support vector machine starts with linear separability, its principle. So in this case here, this can be separated, these two classes. It can also be separated by a line like that, still linear because there's a line that can separate it. This one is not linear because if you draw a line here, this one that's not properly classified. And of course, this one, you need to draw a circle to classify. Okay, so for linear classifiers, it is not just in support vector machine. It's been used by perceptrons or neural network. Okay, so but anyway, the line that we can draw based on this data, okay, can be stated as a linear line where W is the weights and X is the input and B is the bias. Okay, so the in this case here, okay, this line here, if that equation is equal to 0, okay, that means you are on the line. Okay, or that means the point X is on the line. Okay, if the point X is greater than 0, I mean if this is greater than 0, that means X is in this side. Okay, if this function is less than 0, that means X in that side. So that's linear separability. Okay, so in this case, in a two-dimensional form, you can separate them linearly. Given that means your W is already well defined. Okay, your W is good such that they can separate linearly. Well, then the case then is the W. The W is the one that will make this function, okay, this function to make them to separate them properly. Okay, how? Okay, so that means that we need to go through all the W's that can possibly separate them. Okay, before we do that, we say that why W? Because it's the only thing that in this case B is a bias. B can be a part of W, but X are just input data. Okay, we don't have control in X. So W is the one that we are going to find. Okay, including when we say W, including the B. B can be included in W, can be written as part of W. Okay, how? Okay, how? Okay, come on. I should not ask. How? Okay, of course, maybe I shouldn't. Okay, we don't need to. And B and XI 1. Okay, so if you distribute, that's that one. Yeah, and so now, okay, in this case here, this is a vector. So in this case here, we can look at this one instead. Okay, so we separate the variables from this one, but we write it like this so that you can see that it's a line, it's a linear function. Okay, so there are other ways of expressing the linear separability and also the way of expressing even this line function. But for now, let's consider it as a perceptron where, okay, it's here. The B is considered as W0. And then now you can write W wiggle, W tilde, yeah, and consider this one, put them together as your W and your X as your X input together with 1. So now this is your W, the main W, and this is your X. Okay, yeah, they wrote it there. Okay, anyway, so now the way to classify then is to look for the W just like we did before, where this is considered. Yeah, this is now your gradient of your f of x multiplied of this function that you are trying to define. Okay, so anyway, so sine of f of x, I don't know why is this like this, but in this case here, I don't know what is the objective function for them to come out with this gradient function. But anyway, so what is the for sure this is based on the change of w. So if we take the derivative of this one based on the w, you will come out with uh, okay, well, this is the w. Okay, if you change on the w and then based multiplied by xi. Okay, so